Hello, linear algebra students. Today's video lesson is on the topic of applications of matrices. Find the cubic polynomial function that passes through the points depicted in the image below. Okay, so we have 4 points depicted in this image, and we must find a cubic polynomial that will go through them. Now, a cubic polynomial in general form is written as y is equal to some leading coefficient times x cubed plus another coefficient times x squared plus another coefficient times x, and then plus a constant term. So there are 4 coefficients that need to be determined here so that our polynomial will pass through these 4 points. And what we simply do is plug in the x and y values for each point, and we create a system of 4 equations with 4 unknowns. Y is 2 when x is -1. So plug in -1 for all the x's. -1 cubed is still negative, so we'll have negative a. -1 squared is positive, so we'll have plus b. -1 times c will be minus c, and then plus d. So this equation must be satisfied in order to pass through that first point. Now consider the point 1, 1. Well, when y is 1, x is 1. Change all the x's to 1, and this gives us simply a plus b plus c plus d. The third point, 2, 3. Plug in 3 for y. At the same time, you plug in 2 for x. 2 cubed is 8, so we have 8a. And then we're going to have 4b plus 2c plus d. And then finally, plugging in the point 3, 2. Change y to 2. At the same time, you change all the x's to 3. 3 cubed is 27, so we have 27a plus 9b plus 3c plus d. Now I'm going to write the system in matrix form to see what it looks like. Now the variables in our system are a, b, c, and d. And let's write down the coefficients from these 4 equations. The first equation, coefficient of a is -1, coefficient of b is 1, coefficient of c is -1, coefficient of d is 1, etc. Continue. And this is our coefficient matrix. And then we would multiply it by the vector of variables a, b, c, and d, and set this equal to the constant vector, which is 2, 1, 3, 2. Now we're going to use technology to analyze this coefficient matrix and ultimately to resolve this task. Going over to Desmos matrix calculator, I've already typed in the coefficient matrix. Notice that it is square. Therefore, I can calculate its determinant, which I use technology to do, and I get 48. Because the determinant is non-zero, this means that we will have a unique solution to this system. Now, there are a variety of ways we might find that solution. We can use an augmented matrix that we row reduce and put it in reduced row echelon form. Or we can find the inverse of the coefficient matrix and multiply the inverse times the vector of constants. We can do Cramer's rule on this system. We can find an LU factorization and use that as a solving strategy. But using the technology, and since the matrices aren't very large, I'm simply going to have the technology put the augmented matrices in reduced row echelon form. So that means I need to augment this matrix A with another column. So I'm going to click anywhere in the matrix, add a column, and now let's put in that column vector, which is 2, 1, 3, 2. Notice it can't compute the determinant any longer because this is no longer square. But we can do is put this in reduced row echelon form, matrix A, and here we go. So I'm going to copy this over to my work. Okay, so converting this system to an augmented matrix and then row reducing it leads to this result, and we're able to get our answers. Converting these rows back into equations, we simply get that A has to be -7/12, B has to be 2, C has to be 1/12, and D has to be -1/2. So now we can construct the polynomial. Now what I've done is I've graphed these points in Desmos. I graphed the equation y equals ax cubed plus bx squared plus cx plus d, and I added sliders for all of these coefficients. I'm going to reveal that graph, and then one by one I'm going to change the values of a, b, c, and d to what we found. The slider won't let me drag to -7/12, so I'm just going to manually type it in. -7/12 is the value of a. The value of b is 2. The value of c is 1/12. And the value of d is -1/2. And sure enough, we wind up with a cubic polynomial that does pass through the 4 given points. Okay, let's go to the next problem. Another polynomial question. Find the cubic polynomial function that passes through the points depicted in the image below. Now notice that we have only 3 points this time. The 4th point is not given. So this means we're only going to be able to create 3 equations, yet we'll still have 4 unknowns. The 3 equations we create will create similarly to how we did last time. This time, I'll convert to an augmented matrix. It'll look like this. And then use technology to put this in reduced row echelon form. I'll come back up here to our matrix A that we've been working with, and I'll simply remove a row, and it should just remove that last row. Put this matrix in reduced row echelon form, and then I'm going to move this answer to my work. Okay, so the columns represented the coefficients of A, B, C, and D respectively. And notice that we have only 3 pivot positions, which means that D, which is the column that's missing a pivot position, is going to be a free variable. And then converting the rows back into equations, this would read that A minus 1/2 D has to be equal to negative 1/3. And then repeat this for the next 2 rows. And then solve all of these equations for A, B, and C respectively. Okay, so this gives us our solution set, and there's going to be infinitely many solutions. And in Desmos, let's see what this looks like. So this time I only have the 3 points. I type in the general form of a cubic function here. I am unable to specify exactly what these constants should be. In fact, I have to leave D free. So I'm going to leave D as a slider, but I will express A, B, and C in terms of D, just as we did in our work. So A was equal to negative 1/3 plus 1/2 D. B was 3/2 minus D. And C was negative 1/6 minus 1/2 D. And D is unspecified. We'll leave it as a slider to leave it being a free variable. Now let's reveal the graph. And notice that for this choice of D, when D is 1, I have a graph that passes through the 3 points. But now I'm going to play the slider, and you can see that as we pick different choices of D, we simply get different cubic graphs that do happen to pass through these 3 points. So there are infinitely many possible answers here. Okay, let's go to the next problem. A total of 350 tickets were sold to a high school play. The total revenue was $3,284. The price per ticket of each kind of ticket is shown below. Find the number of tickets of each type sold. Okay, so that we have adult tickets at $10 each, senior tickets at $8 each, and child tickets at $4 each. We need variables to represent the number of tickets of each type. We could use ASC or XYZ or whatever variables you choose. Let's use A, S, and C to stand for these 3 different types of tickets. So we know that the number of adult tickets plus the number of senior tickets plus the number of children's tickets should equal 350. Furthermore, we know that if I sell A adult tickets and they're $10 each, I will earn 10 times $8. Similarly, I'll earn 8 times S dollars selling the senior tickets, and I'll earn 4 times C dollars selling the children's tickets. And this should equal our total revenue, which is $3,284. Now it appears that these are the only 2 equations I can create from the information in this prompt. I'm going to write this as an augmented matrix. We'll put the coefficients of A, then S, then C in the same order I have the equations. So we have 1, 1, 1, and 350. And then we have 10, 8, 4, and 3,284. And this is an augmented matrix. Notice the coefficient matrix right here is not square, so we cannot calculate a determinant. So either this will be inconsistent or we are going to have infinitely many answers. I'm going to go ahead and do this one by hand. I'm going to multiply top row by negative 10, add it to the second row. This is going to give me a new matrix. Now I'm going to multiply the bottom row by negative 1/2. I have 2 pivot ones, but I need all the entries in those columns to also be 0. So I now need to target this position here. That needs to be a 0. So I'm going to multiply the bottom row by negative 1 and add it backwards up to the top row. And this should complete our reduced row echelon form. Okay, the columns were the coefficients of adult tickets, senior tickets, and children's tickets, and the leading entries are in the A and S columns. So the number of children's tickets is a free variable, and converting the rows into equations, we get that A minus 2C has to equal 242, and S plus 3C has to equal 108. Solving these for A and S, A has to be 242 plus 2C, and S has to equal 108 minus 3C, and C is free. This would be the solution to this system. Now let's think about it in the context of this problem. There are infinitely many answers to this dilemma, suggesting that we do not have enough information to know exactly how many of each type of ticket that was sold. You would need extra information or a third equation in order to resolve this. For example, suppose that someone in the crowd was able to count the children and saw that there were only 10 children in the crowd. Then you could say that C is 10, and then once you know that C is 10, you'd be able to calculate what A and S have to be in order to have both equations satisfied. But suppose that someone claimed that 50 children tickets were sold. Well, this would be an interesting thing to think about, because S is equal to 108 minus 3C. And if we try to substitute in 50 for C, notice what it would happen to S. S would be equal to 108 minus 150. That would give me a negative 42, suggesting we sold negative 42 senior tickets, which doesn't make sense. So we know that C cannot be 50. In fact, knowing that all of these variables only make sense if they are positive, we could make the following claim, that S, which equals 108 minus 3C, has to be bigger or equal to 0. We can solve this for C. It means that we have 108 is greater than or equal to 3C, and divide both sides by 3, and we get C has to be less than or equal to 36. So 36 would be the maximum number of children's tickets that could have been sold. Otherwise, we have an impossible scenario. But as it is, there's not enough information to know exactly how many of each type of ticket was sold. We would need extra information. Okay, let's go to the next page. A network of one-way roads connects the four intersections below, the intersections being A, B, C, and D. Each value in the diagram represents a flow rate in cars per hour. Assume at each intersection the flow rate in must equal the flow rate out. Find the flow rates for the 5 missing roads so that the traffic flow is balanced. Okay, so the flow rate into intersection A and into intersection B and out of intersection C and out of intersection D are known. But the 5 interior one-way roads, we do not have flow rate information for those. Let's label these 5 with some variables to represent the flow rates for each of these 5 one-way road segments. Let's say the roadway connecting A to C has a flow rate of U, connecting A to B has a flow rate of V. The diagonal B to C, let's say it has a flow rate of X. C to D is a flow rate of Y, and D to B is a flow rate of Z. Okay, so the flow rate into an intersection must equal the flow rate out. So let's focus on intersection A first. Looking at intersection A, we know that there's a flow rate in of 80 cars per hour, and the flow rate out, there's 2 different roads leading out of intersection A. That would be the flow rates U and V, and they would be added together to equal the flow rate out. Now let's focus at intersection B. There are 3 flows into intersection B. One of them is known, so 115. Also, we have to add to that the flow rate V and add to that the flow rate Z. We have 3 different roads leading into intersection B, and all of this flow rate in has to equal the flow rate out. So road X is the only way out of intersection B. Let's look at intersection C. The flow rates in are U and X, so U plus X, and the flow rates out are 95, which is known, and Y. And then finally, let's look at intersection D. The flow rate in is Y, and the flow rates out are 100 and Z. All right, so this creates a system of equations. Notice we have only 4 equations, but there are 5 unknowns. This would suggest a non-square coefficient matrix. I'm going to rewrite these equations so I have the variables on the left and the constants on the right. And let's go in the order where we have u, v, x, y, z. So the first equation is basically saying that u plus v has to equal 80. So that one I'm just moving the 80 to the right side instead. The next equation, I'm going to move both these terms to this side over here. So we would have a negative v. There's no u though. We do have a positive x. There would be a negative z, and this would have to equal 115. The next equation, this time I'm going to leave the variables on this side. I'll move this y over and set everything equal to this 95. We have one u, we have no v's. We do have a positive x. We would subtract the y, and this would have to equal to 95. And similarly for this last equation, I'm going to put the variables to the left side. So this z I'm going to subtract over and leave the 100 on the right. So we would have no u's, no v's, no x's, but there would be a y, and then minus a z, and is equal to 100. Now there is some freedom here in how you did this. Basically, you could have moved things to other sides of the equations, and that would simply have the effect of basically multiplying one of my equations by -1 on both sides. It doesn't matter. There's lots of ways you might have set this up. But now that we have all the variables on one side and all the constants on the other side, I can consider an augmented matrix. And let's go again in the order of u, v, x, y, z. So writing down the coefficients of the four equations gives us the following. And now writing down the constants. And now I'll use technology to put this in reduced row echelon form. All right, Desmos gives us the following reduced row echelon form for this matrix, which I'm going to now move over to my notes. Okay, now let's identify the pivot positions. There's a pivot position here, here, and here. This suggests that x and z are both free. And then converting our rows back to equations and solving for the pivot position variables, we get the following. Okay, the solution to our system is right here, where we have x and z are both free, and u, v, and y depend on our choices of x and z. Now we do have to take into account that x, y, z, u, and v all represent positive flow rates. Therefore, there are some limitations on what I can choose. I'm not free to choose negative values for x and z, for example, and I also have to refrain from choosing positive values for x and z that might lead to negative values for the other three variables. Let's read this next sentence here. If the road from intersection A to C is closed, find the minimum value of the flow rate of the road connecting intersections B and C. Looking at our image, so let's assume that A to C is closed. So that means the flow rate U would be 0. And then this question is asking us to consider what would be the minimum value then acceptable for this flow rate connecting B to C, so the minimum value of x. Let u be 0 and look at our first equation. So that would give us 0 is equal to 195 minus x plus z. Solve this for x, so add x to the other side, and we get x equals 195 plus z. Now keep in mind that z has to be bigger or equal to 0. So the smallest z would be 0, which means that the smallest x would be 195. And this would be, of course, cars per hour. An alternate thing we could have done here is if the road from A to C here is closed, that means we would not have any u's involved in our equations. So basically this whole first column would be wiped away, which means we could reanalyze the problem using a different matrix. So I've copied the matrix below. I'm going to get rid of that first column and then use technology to put this matrix into reduced row echelon form. This is the matrix we're calling matrix B in my work, and then putting matrix B into reduced row echelon form, we get the following result, which I'll copy over to my work. So our pivot positions are here, here, and here, which means that z is a free variable. And translating the second row into an equation would read x minus z equals 195, which suggests that x has to be equal to 195 plus z. And notice that gives us the same result that we got over here. Okay, let's go to the next slide. This problem is about chemical reactions. Mass balance theory states that we cannot create or remove atoms within a chemical reaction. So this is when two compounds are combined, have a reaction, and produce two new compounds. Find the amounts of each compound that must be used and created so that the chemical reaction below is balanced. All right, so we have some sort of compound here that has 3 atoms, a compound here, and they combine together, have a chemical reaction, and they produce 2 new compounds. You might recognize that fourth one, H2O, so that's water is one byproduct of this reaction. Now these letters, let's remind ourselves of what they are. K is potassium, O is oxygen, H is hydrogen, and P is phosphorus. And you might recall from a chemistry class, when it says H3, this means there's 3 hydrogen atoms in this compound. There's 4 oxygen atoms in that compound, etc. Okay, so what we don't know is how many of each compound is required so that this equation is even possible, because we cannot lose atoms or gain atoms in the process. So we're going to put 4 variables involved. We have an unknown number of the first compound plus an unknown number of the second compound, and that needs to produce some number of this compound plus some number of this compound without losing any atoms or gaining any atoms. So let's keep track of the 4 elements, how much there would be. Let's keep track of potassium. On each side of the equation, if we have A compounds of KOH and each compound has 1 K, then we would have a total of AKs involved on the left 2 compounds. And this would have to equal the number of potassium atoms we have on the right side. Well, this compound has no potassium. We only have potassium right here, and we have C molecules of this compound, and each molecule has 3 potassium atoms. So that means we would have 3C potassium atoms on the right side of our equation. Now let's move to the oxygen. We have oxygen in a variety of places in the left side. We have 1 atom of oxygen here, and we have 4 atoms of oxygen here. And so A molecules with only 1 oxygen atom would mean we'd have A atoms of oxygen from the first compound plus, and then we would have 4 times B atoms of oxygen from the second compound. And this would have to equal the number of oxygen atoms on the right side of our equation, which would give us 4C plus 1D. Okay, now let's focus on the hydrogen. We have 1 hydrogen atom here, and we have 3 hydrogen atoms there. So that means we're going to have A hydrogen atoms from the first compound plus 3B hydrogen atoms from the B copies of the second compound is equal to, now our hydrogen atoms on this side, there's no hydrogen in the first molecule or first compound, but we have 2 hydrogen atoms here, and we have D of those molecules. So that would be 2D hydrogen atoms on the right side. And then finally, let's do our phosphorus. Keeping track of the phosphorus on each side of this equation, we would have only 1 phosphorus atom here and only 1 phosphorus atom there. That's it. So you would have B atoms of phosphorus on the left, and we would have C atoms of phosphorus on the right. So B would have to be equal to C. Okay, this creates an equation that has 4 unknowns, A, B, C, and D, and there's 4 equations. So this is going to create a square coefficient matrix. Let's go ahead and convert these equations. I'm going to put all the variables on the left. So we had A minus 3C is equal to 0. We would have A plus 4B minus 4C minus D has to equal 0. We have A plus 3B minus 2D has to equal 0. And then we would have B minus C has to equal 0. Converting this to an augmented matrix gives us the following, where the columns will correspond to A, B, C, and D. And then the constants are all 0 on the right. This was a case where we called this a homogeneous linear system because we have zeros all on the right. This structure is a coefficient matrix times a vector is equal to the 0 vector. And if the coefficient matrix is square and invertible, then we know that this will only have the trivial solution. If the only solution to the system is going to be the x vector is equal to 0, that would suggest A, B, C, and D all have to be 0, which would suggest that maybe this chemical reaction isn't possible. Going to our Desmos calculator, I typed in just the coefficient matrix, which is a 4x4 matrix, and calculated its determinant. Notice its determinant is equal to 0. So from our theory about the invertibility of A, we know that if the determinant of A is 0, then A is singular, and we know therefore that AX equals 0 is going to have infinitely many answers. It'll have answers that are not just the 0 vector. Okay, let's go ahead and put this in reduced row echelon form. I'll go back to our calculator. Let's add 1 more column to create an augmented matrix. We just need zeros there, so we'll hit enter. And then can't calculate the determinant of the augmented matrix anymore because it's not square, but I can do the reduced row echelon form, RREF, of matrix A. And let's convert these to fractions. And here's what we get. I'll convert this over to our notes. Okay, our pivot positions are here, here, and here, suggesting that D is a free variable because it does not have a pivot position in its column. And then going to convert these rows into equations and solve them for A, B, and C. And we get the following. So this is our solution, and there's infinitely many answers. D can be anything. However, this context only makes sense if A, B, C, and D are whole numbers. So what does it mean to have half of a compound? We don't really want that. We want A, B, C, and D to all be whole numbers, which means I should probably limit myself to choices of D for which 1/3 of D is going to be a whole number. For example, the smallest such choice would be what if D is 3. If D is 3, then we would have that A would be 3, B would be 1, C would be 1, and D would also be 3. So 3 of this compound plus 1 of this compound produces 1 of this compound and 3 water molecules. And this would be balanced. No atoms would be lost or gained in that process. And then we can scale these numbers by any amount. So if, for example, if we double all these numbers, that would correspond to D being 6. So if D was 6, then that would mean that A is also 6, B is going to be 2, C is going to be 2, and D will be 6. And so we could also do 6 of these compounds plus 2 of these will produce 2 of these and 6 of these. And there's really infinitely many answers, but we should limit ourselves to choices of D that lead to A, B, C, and D all being whole numbers. Okay, let's go to the final slide. This is an application of electrical circuits. Find the current of each of the 3 circuits in the electrical diagram below. So down below we have 3 circuits. Here's a circuit here, and a circuit here. And we want to find the currents. The current is the flow in electrons per second. Let's do a little reminder of the relevant quantities in analyzing circuitry and some of the laws governing how we're going to create equations. Reading here, we're going to use capital I to stand for the current or the flow of electric charge, and it's measured in amperes, or we can say amps, or we can use the capital A as an abbreviation of that unit, with 1 amp approximately equal to 6.24 times 10 to the 18 electrons per second. So this measures basically how quickly electricity is passing. V will stand for the voltage, which is the force of the electrical current, and it's going to be measured in volts, and we'll use a V for that. R is the resistance of a resistor, measured in ohms, and we use the Greek letter omega to represent ohms. And a resistor is something that drains voltage. For example, electricity passing through a light bulb, voltage gets drained in order to create the light. Now, Ohm's law suggests that the voltage drop at a resistor is equal to, the voltage is equal to the current times the resistance. So it's going to be I times R. And then Kirchhoff's voltage law suggests that the total volts dropped through a circuit will equal the sum of the voltage sources. Looking at this diagram, I can see 1, 2, 3, 4, 5, 6, 7, 8 total resistors. These are drains on your voltage. So we need sources of voltage, and that's what these symbols are. These represent sources of voltage. We can think of them as batteries. The amount of voltage supplied by each battery is indicated by the numbers, 30 volts, 5 volts, and 20 volts. Furthermore, the natural flow of electricity through a battery, it flows from the positive terminal of the battery. So voltage would attempt to flow this way. In this case, flow this way in this case, and flow this way in this case. Now we said that there were 3 different currents, one for each circuit. We're going to call those currents I sub 1, I sub 2, and I sub 3. Now we have to set up the equations based off Ohm's law and Kirchhoff's voltage law. Now we can assume that the flows will be any direction we want, counterclockwise or clockwise. And if in the end, if we discover that a flow is negative, then it would simply imply that it's the opposite the direction we initially assumed. For example, I could begin this problem by just assuming all of these flows are going to be in a counterclockwise direction through the circuit. Let's just make that assumption off at the start, and then we'll create equations based off these assumptions. And then later we'll discuss what if I change some of these original assumptions and see how that affects my setup. So looking at the first circuit, we are assuming a flow in this direction around that circuit. Each resistor is going to drain voltage, and there's 3 resistors in this circuit. And Ohm's law suggests that the voltage drop is going to be calculated by doing the current times the resistance. So the current is represented by the I, and the resistance are the omega values. And so in the first circuit, we would have 4 times I1 would be the amount of voltage drained by this first resistor, plus 3 ohms times I1 drained by that resistor, and then plus 4 ohms times I1 is the amount of voltage drained by that resistor. Furthermore, we have to take into account that there are a couple of resistors here that are on multiple circuits. For example, this resistor right here is also on the middle circuit that involves I2. And notice that I2 flows this way based on our assumption of a counterclockwise motion. We're assuming I2 flows to the left through that resistor, whereas I1 flows to the right through that resistor. So we have a different direction flow. So what we have to do is remove from this the voltage drop caused by the resistor with regards to the second current. So that's going to be 3 ohms, but times I2. The other 2 resistors do not share circuits. So this equation gives us the total relative voltage. It should be equal to the voltage source. Now, up here with our battery, notice that we assumed that we are moving counterclockwise, which would suggest a flow through the battery this way, which is the normal direction given where the positive terminal is. And so in this case, we would put a positive 30 volts, and this gives us our first equation. Now let's look at the middle circuit. In the middle circuit, we have 1, 2, 3, 4 resistors as we go counterclockwise through there. So that's going to be, we have 1 ohm times I2, plus 1 ohm times I2, plus another ohm times I2, and then plus 3 ohms times I2. 2 of these resistors also involve 2 other circuits. So let's focus on that top one first. I2 flows this way through that resistor, but I1 flows the opposite direction through that resistor. So we need to remove 3 ohms times I1 to account for that. Now in this resistor, we have I2 flowing this direction through that resistor, but I3, given that we assumed it was counterclockwise, is flowing the opposite direction through that resistor. So we have to remove also 1 ohm times I3, so just remove I3. Now in this circuit, we do have a voltage source and a battery. And given the counterclockwise assumption, this flow is in the expected direction through that battery. So the voltage expression on the left should be equal to a positive 5. And now let's analyze the third circuit. As we flow through, third circuit flows through 3 resistors, 1, 2, 3, and we're assuming in a counterclockwise direction. So it's going to be 1 ohm times I3, so just I3, plus another ohm times I3, plus a third ohm times I3. The top resistor is part of the middle circuit, and we're assuming that I3 flows through that resistor this direction, but I2 flows the opposite direction. So we need to remove from this 1 ohm times I2. And this voltage expression should be equal to what we get from the voltage sources. And on this circuit, there are 2 different batteries. Also, we are assuming that we are flowing counterclockwise, which means that we're flowing counter, in both cases, counter the natural flow. Therefore, both of these should be considered negative voltages. So we would have a negative 5 and then a negative 20. Okay, now we're going to convert this to an augmented matrix and then use technology to put this in reduced row echelon form. And our 3 variables will be I1, I2, and I3. So all of the I1s from equation 1, there's these 3 terms, they add to be 11 I1s. So we have 11. And then there's a minus 3 I2 and no I3s. And then augment the matrix, and this will be equal to the voltage of 30. The second equation, find the I1s. I see a single I1 right here, then the I2s, and then a single I3. So we have a negative 3 I1. All the I2s add to 6 I2s, and then we have that negative 1 I3, and all of this is equal to a voltage of 5. And now looking at our third equation, we have no I1s, we have a negative 1 I2, and we have 3 I3s, and this is equal to a voltage of negative 25. We'll use technology now to convert this to reduced row echelon form. First of all, notice that the coefficient matrix, which is square, has a determinant that's not 0. Therefore, we know that this will have a unique solution. So I'm going to go back up to A and augment it by adding a column. And now let's put in the constant vector, which was 30 and 5 and negative 25. The determinant of this matrix no longer makes sense because A is not square, but let's go ahead and put it in a reduced row echelon form, and we get the following result. This suggests that the first current is I equals 3 amps. The second current is I2 is equal to 1 amp. And the third current is negative 8 amps. Now the ones that are positive mean that our assumed directions were correct, and the third current that's negative suggests that the electricity will flow in the opposite direction of our assumption, which means that in reality, current 1 goes counterclockwise 3 amps, because we assume counterclockwise to begin with. Current 2 also goes counterclockwise, the flow rate of 1 amp, but current 3 is going to go clockwise at a flow of 8 amps. Okay, now let's just quickly examine what this would look like if I had assumed different directions at the start. Let's assume that I1 is going to be clockwise to begin. We'll leave I2 counterclockwise, but let's also change the direction of I3 to clockwise. Let's see how this affects our equations. So looking at I1, there's still 3 resistors. We have 4I1, 4I1, and 3I1. So that's going to be a total of 11I1. Let's examine the shared resistor right here. Given my assumed direction of flow, we have I1 passing through this resistor in this direction, but then notice that's also the direction that I2 is passing through it. So when they go in the same direction, we add the I2 resistance, which should be 3 ohms times I2. Also notice that our battery, we're assuming a flow in the opposite direction of what the battery would indicate. And so this will be equal to a negative 30 volts. Okay, let's look at the middle circuit. Again, I still see a total of 4 resistors in the middle circuit. So we have 3I2 plus 1I2 plus 1I2 plus 1I2. That's still going to give me 6 I2s. Now let's look at the shared resistors. We have a shared resistor here, and I2 is flowing this way through it, but so is I1, at least by assumption. So we need to add 3 ohms times I1 to this. So add 3 I1. Now let's look at the other shared resistor right here. We have I2 flowing through it this way, but also we're assuming I3 is flowing through it the same direction. So we get to add 1 ohm times I3 to this. So plus 1 copy of I3. Now let's see what voltage this will be equal to. We have a single battery in this circuit right here. And notice that our assumed direction of flow is in the expected direction through that battery. And so this would be equal to a positive 5 volts. Okay, finally, let's look at the third circuit. I still see there are 3 resistors, and they all have ohms of 1. So we have 1I3 plus 1I3 plus 1I3. It will give us 3I3. Now let's focus on the shared resistor. We're assuming I3 is flowing through that resistor this direction, but I2 is flowing in the same direction by assumption. And so we get to add 1 ohm times I2. So just add I2. Now let's look at our flow through the battery sources, through the voltage sources. We're assuming flow this direction through that battery, which is the expected direction, and this direction through that battery, which is the expected direction. So both of these voltage sources should be positive. So we'll have 20 plus 5. We should have, therefore, 25 positive. Okay, convert this to an augmented matrix as follows. And I'm noticing a typo right here. Maybe you saw it earlier, but that needs to be I1. and now convert this to an augmented matrix. And now we'll use technology to convert this to reduced row echelon form. Over here, this is the matrix that I'm calling matrix B, and I put that in reduced row echelon form, and I'll move that work over to my notes now. All right, so this gives me that I1 has to be equal to -3 amps, I2 is equal to 1 amp, and I3 is equal to 8 amps. So the two answers here that are positive suggest that our assumed directions were correct. So in other words, looking back over here, we assumed I2 was counterclockwise. Turns out that assumption is correct. So circuit 2 goes counterclockwise at the rate of 1 amp. Circuit 3 flow is also positive 8, so it means our assumption is correct in that circuit 3 should go clockwise. But circuit 1 is a -3, which means our assumption is in the wrong direction. So we assumed that circuit 1 was going clockwise, but we need to make it go counterclockwise instead at the rate of 3 amps. So you'll notice that even though we had different assumptions at the start, our final results and our interpretations of the negatives lead to the same conclusions, regardless of the directions that we assumed of the currents at the start. Okay, and this wraps up our lesson on applications of matrices.